So two-way ANOVA is a little bit more complicated than the standard one-way, where you're just comparing between differences between means, because you've got another categorical variable that can affect the way you get your results. This is the first time that I have to talk about the general linear model. This is a more complicated variation of regression. So for example, if I did regression lines and there was different slope of height against weight for men and women, that is called ANCOVA, analysis of covariance, and that's another example of a general linear model. For a two-way ANOVA, it's assumed that the two factors combine together in a linear way, so they add to each other. So if one gives a certain amount of change and the other one gives the similar amount of change, then the two added together would give double amount of change. So what you have to do is take into account interaction effects. Now I could actually have done the one-way ANOVA using a general linear model. So if I took the compost data that we had before and I fed it into a general linear model, this is the table that I would get. So what you have is a column that says sum of the type 3 errors of squares, the degrees of freedom, the mean square difference, the f value and the sig value. So in that case, the effect of compost, the f value is 5.755 and the sig value is 0.03. Which, when you do it using the one-way ANOVA, you've got the between groups. The sum of the squares was 26.876, degrees of freedom was 3, mean squared difference 8.959, f was 5.755. So you've got exactly the same data in the general linear model table that you had before, only you've got extra factors as well. So you've got intercepts and model corrections and errors. Now the way it's working is as a form of regression. If you plot the mean of each of the groups of the amount of weight of the plants for each of the different composts, if there was no difference in the means between all of the different groups, then the observed total mean would be the same as each of the means from each of the different groups. Now here you can see that one group's above, one group's below, one's just a little bit above the mean, one's a little bit below the mean. So that's telling you that you haven't got a horizontal straight line, which is what you're looking for in a one-way ANOVA. You can also do the post hoc tests between the composts in the general linear model as well, and you get exactly the same sort of table as you would if you were doing it in the one-way ANOVA. Now for two-way ANOVA, we're going to use a related set of data for Cosmos plants, and there's two varieties which are called Pip and Christopher, and they're split across the same four composts as before. So now there are two things that can interact with each other: the variety of the plant and the composts. It's called a univariate general linear model because there's only one response variable, which is the weight of the plant, or in this case it's the height of the plant. Once you place the data into the general linear model, this is the general linear model table, the output from it. So here you've got the first two lines we don't really have to worry about, the corrected model and the intercept. The intercept is the same as the constant in your linear regression, and it's usually a meaningless thing, so it can be ignored. The things that matter are the compost and the variety, and the compost multiplied by the variety. You need to find out which of these things is making a significant difference. So you look at the value of f and you look at the sig values. So for the compost, you can see that the value of f is 1.289 and the sig is 0.285. This is not significant because it's not below the threshold of 0.05. When you look at variety, the f is 39.255 and the significance is 0. So this is definitely important. The difference between the heights of the two plants in this particular model is dependent on the variety much more than anything in the compost. And compost times variety gives an F value of 2.475 and a sig of 0.068. Now, the issue with this is you've already found out that compost is not making any significant effect. Variety is making a much more significant effect. So the largest part of that composite is going to be a residual part coming out of the variety. And it's not, the p-value for it is 0.068 and not below 0.05. So this suggests that compost times variety is also not significant. So how do I do a GLM? So I go into SPSS, I go to Analyze, and I go for General Linear Model, and I get this and Univariate General Linear Model, and I get this particular set of boxes. So I have, as with all regressions, a dependent variable. Then I don't have an independent variable, I have different types of independent variables. I have fixed factors, things that are assigned and cannot be changed. And I have random factors, which are things that are changing just because of the nature of the object, nature of the material. Now in this case, the dependent variable is the height of the plant. And I've got two fixed factors, compost and the particular variety of the plant. So I need to put those two in. Now as well as that, I've got choices of model, contrast plots, post hoc, EM means, so that's the marginal mean values, the mean that is affected by a single one of the fixed factors. So if I go to EM means, I can display the means for the compost that depend on compost, that depend on variety, and that depend on compost times variety. And if I click on compare main effects and do Bonferroni, this will give me the post hoc analysis that I want. What I can do is plot the estimated marginal means, the things I've just calculated, the EMs, for the two different varieties. Now if there is a significant difference between the two different varieties, then these two plots will not overlap with each other. So what I've done is put on there the 95% confidence interval. So on the first compost there is an overlap between the two, but on compost 2, 3 and 4 there is no overlap between the two different varieties. So variety is making most of the difference between the two groups. If I look at the pairwise comparison between the two, I can see that there's a significant difference between the two varieties, and I can see that the confidence bound for the difference is between 3.759 and 7.266. It becomes minus 7.266 and minus 3.759 depending on which one I subtract from the other. There's also the univariate test at the bottom showing the F value to be 39.255 and a p-value of 0 for that particular comparison. And for the post hoc tests, these are the differences between all of the different composts. And as you can see, there's none of them that turn out to be significant. Because pretty much you can see from the graph that there's, apart from perhaps compost 1, they completely overlap with one another. So there's the univariate test where you're keeping the variety fixed and you're just looking at the compost composition. So the F was 1.289 and the sig was 0.285.